Hello and welcome. Yesterday, December 5th, astronomers working with the Atacama Large Millimeter Array Telescope in Chile's high desert announced something extraordinary. They detected methanol and a suite of carbon-containing compounds in Comet 3I Atlas, and the concentrations they found are higher than anything we typically see in solar system comets. That alone would be news. But this is no ordinary comet. 3I Atlas is interstellar. It came from beyond our sun's gravitational influence, from another star system entirely, and it is currently sweeping through our neighborhood on a hyperbolic trajectory that will eventually carry it back into the void. What makes yesterday's announcement critical is this. Those organic molecules, methanol included, are precisely the kinds of compounds astrobiologists believe could have seeded early Earth with the chemistry necessary for life. We are looking at a visitor from another stellar system carrying the building blocks of biology. If you want to stay updated as this story develops, because it is developing rapidly, make sure to subscribe and turn on notifications. This is going to be a long and detailed investigation, and new data is coming in almost daily. Let me set the stage. For decades, we assumed comets were local phenomena. They formed in our solar system's outer regions, the Kuiper Belt or the Oort cloud, and occasionally got nudged inward by gravitational perturbations. Then, in 2017, we detected 1I/Oumuamua, the first confirmed interstellar object. It was strange, elongated, accelerating in ways we could not fully explain, and it left before we could study it properly. 2 years later, Comet 2I/Borisov arrived, and that one behaved more like a textbook comet. It had a coma, a tail, it was outgassing, and its chemistry looked familiar. We could breathe a little easier. Interstellar objects, it seemed, were not all mysteries. But 3I Atlas is different. It is active, yes, but its chemical signature is unlike anything we have catalogued in our own comets. The ALMA observations show elevated methanol, along with other carbon compounds, and that is a red flag. Methanol in comets is not rare, but the concentrations here are anomalous. They exceed what we see in local comets, and that raises an immediate question. What does the chemistry of a comet tell us about the stellar nursery where it formed? If 3I Atlas has more methanol, does that mean its home system had different temperatures, different radiation environments, different molecular cloud conditions? And if so, what does that imply about the diversity of planetary systems across the galaxy? Let's look closer at the data. The ALMA telescope operates at millimeter and submillimeter wavelengths, which are ideal for detecting cold molecules in space. When a comet outgasses, the molecules in the coma emit radiation at specific frequencies, and ALMA can pick those up with incredible precision. On December 5th, the team observed emission lines corresponding to methanol, formaldehyde, and other carbon-bearing species. The signal strength indicated concentrations well above the baseline we have established for comets like Hale-Bopp or 67P/Churyumov-Gerasimenko. But ALMA is not the only instrument watching. Spectroscopic observations from the 1.3-meter Araki telescope at the Koyama Observatory in Japan have added another layer of complexity. The Japanese team detected emissions of CN, that is, cyanogen, C3, which is a carbon chain molecule, C2, another carbon species, and atomic oxygen. All of those are expected in an active comet. But here is the crucial detail. The NH2 emission, which corresponds to ammonia radicals, was weak, much weaker than we would expect. In typical solar system comets, NH2 is a strong tracer because ammonia ice is common in the outer regions where these objects form. The fact that 3I Atlas shows weak NH2 but strong carbon emissions suggests a different formation environment, one where carbon chemistry dominated over nitrogen or ammonia-rich ices. This contradicts what we previously thought about cometary composition being relatively uniform across different stellar environments. It implies that the molecular cloud where this comet originated had a different chemical recipe, possibly due to variations in temperature, radiation from nearby stars, or the timing of ice condensation during the protoplanetary disk phase. Now, on November 30th, the Hubble Space Telescope captured images of 3I Atlas, and those images were released publicly on December 5th, the same day as the ALMA announcement. Hubble's resolution is unmatched in the optical range, and what it showed was striking. The comet has a well-developed coma, the cloud of gas and dust surrounding the nucleus, but it also displays what astronomers call an anti-tail. That is an elongation of material pointing toward the sun, not away from it. At first glance, that sounds impossible. Radiation pressure from the sun pushes dust and gas away, forming the classic tail we all recognize. So, why would material extend sunward? The explanation involves perspective and dynamics. What we are seeing is not a true tail pointing at the sun, but rather a trail of larger, slower-moving particles that have been left behind as the comet moves along its orbit. From our viewing angle here on Earth, that trail appears to project toward the sun. Astrophysicist Avi Loeb, who has been following this object closely, has suggested that this anti-tail could be a swarm of solid, non-volatile particles, ejected from the nucleus, and now drifting at a distance of roughly 60,000 kilometers. Loeb's models indicate these particles are not being driven by gas pressure alone. Instead, they may have been ejected by non-gravitational forces, possibly related to the comet's spin or asymmetric outgassing. If chunks of ice sublimate on one side of the nucleus more than the other, the resulting jet can act like a thruster, changing the comet's velocity and ejecting solid fragments in the process. This is consistent with what we have seen in other comets, but the scale here is larger and the particles appear to be more substantial. The Hubble images also show evidence of cryovolcanism. That is a term we usually reserve for icy moons like Enceladus or Europa, where subsurface oceans erupt through cracks in the ice shell. But comets can exhibit similar behavior. As 3I Atlas approaches the sun, solar heating causes subsurface ices to sublimate rapidly. Carbon dioxide ice, in particular, can transition directly from solid to gas at relatively low temperatures. When that happens beneath the surface, pressure builds up, and eventually the ice ruptures, releasing a jet of gas and dust. We have observed this in comets like Hartley 2 and Tempel 1. What is remarkable about 3I Atlas is the intensity and frequency of these eruptions. The coma is evolving rapidly, with multiple jets visible in the Hubble images, suggesting that the nucleus is highly active and possibly heterogeneous in composition. Some regions may be rich in carbon dioxide ice, others in water ice or methanol ice, and as different layers get exposed to sunlight, we see bursts of activity. This creates both a gas tail, driven by ionized molecules interacting with the solar wind, and a dust tail, composed of heavier particles pushed out by gas pressure. For observers in the southern hemisphere, the comet is currently visible in the constellation Virgo, near the star Zavijava, and it can be spotted with a 6-inch telescope. That level of brightness is impressive for an interstellar object, and it speaks to the comet's size and activity level. So, what does this actually mean? Yesterday, December 6th, NASA released an updated analysis, and the headline is astonishing. They estimate that 3I Atlas is over 7 billion years old. To put that in perspective, our solar system is 4.6 billion years old. This comet was already wandering through interstellar space for more than 2 billion years before our Sun even ignited. It predates the Earth, predates the planets, predates everything we consider part of our cosmic neighborhood. It is, as far as we know, the oldest confirmed interstellar object ever detected. That fact alone forces us to reconsider the timeline of galaxy evolution. How many of these ancient wanderers are out there? How long do comets survive in the harsh radiation environment of interstellar space? And what does their chemistry tell us about the early epochs of star formation, back when the Milky Way was younger and more turbulent? The nucleus diameter is estimated to be somewhere between 440 meters and 5.6 kilometers. That is a wide range, and it reflects the difficulty of measuring a distant, irregularly shaped object surrounded by a bright coma. The uncertainty comes from assumptions about the nucleus's albedo, or reflectivity. If it is dark, like most cometary nuclei, then the larger estimate is more likely. If it is brighter, perhaps due to fresh ice exposure, then the smaller estimate fits better. Either way, we are dealing with a substantial object, potentially billions of tons of primordial ice and rock. The first detailed images at close range came from spacecraft operated by NASA and ESA, captured when the comet was 29 million kilometers from Mars. That is not a flyby in the traditional sense, but from that vantage point, the spacecraft could resolve features we cannot see from Earth. The images confirm that 3I Atlas is in an active phase. There is a distinct plasma tail, glowing blue-green from ionized carbon monoxide and other molecules, and there appears to be a secondary dust tail as well, though the dust component is fainter. Physicist Brian Cox commented on the significance of this discovery, emphasizing that the comet may have been drifting through the galaxy for eons, a silent witness to the formation of countless stars and planetary systems. It could have passed near supernova remnants, through molecular clouds, across spiral arms, accumulating cosmic ray exposure and interstellar dust particles. The fact that we can now study it in detail is a testament to how far astronomy has come. Just a few decades ago, detecting an interstellar comet would have been impossible. Now we have multiple telescopes, both ground-based and space-based, coordinating observations across the electromagnetic spectrum. The European Space Agency's JUICE spacecraft, currently en route to Jupiter, has also turned its instruments toward 3I Atlas. JUICE carries a suite of spectrometers designed to study the composition of icy moons, and those same instruments are well suited for cometary science. Preliminary spectroscopy confirms the comet's activity, showing emission lines from water vapor, carbon monoxide, and carbon dioxide. The full dataset will not be available until February 2026, but the early results are consistent with the ALMA and Hubble findings. By the end of December, the comet will have moved into the constellation Leo, where it will remain visible in the morning sky, though its brightness will gradually decrease as it moves away from the Sun. For amateur astronomers, this is a rare opportunity to observe an interstellar object with backyard equipment, something that may not happen again for years or even decades. Scientists are now focused on the comet's closest approach to Earth, predicted to occur on December 19th at a distance of approximately 270 million kilometers, or 1.8 astronomical units. That is nearly twice the distance from the Earth to the Sun, so there is no danger of impact or even close passage. But it is close enough for detailed spectroscopy, high-resolution imaging, and potentially even radar observations. The Arecibo telescope is gone, but the Goldstone and Green Bank facilities can still attempt radar ranging if the comet's brightness and trajectory cooperate. The hope is that increased solar heating will trigger even more vigorous outgassing, releasing fresh material from the nucleus interior. If that happens, we may see a temporary brightening, possibly even a short-lived meteor shower if any fragments enter Earth's orbit. The probability of that is low, but not zero. Fragments from 3I Atlas would have a different composition than typical meteoroids, and if any survive atmospheric entry, they could provide direct samples of interstellar material. Imagine holding a rock that formed in another star system, that traveled across light years of space, that predates our Sun. That would be revolutionary. Astrobiologists are particularly excited. Elizabeth Rivera from NASA's Astrobiology Institute has stated publicly that analyzing the organic compounds in 3I Atlas could help answer one of the most profound questions in science. Could comets like this have delivered the molecular precursors for life to early Earth? We know that Earth was heavily bombarded by comets and asteroids during the first billion years of its existence. We know that those impacts delivered water, possibly forming the oceans. But did they also deliver complex organic molecules? Amino acids, nucleobases, sugars, the raw materials for RNA and DNA? Laboratory experiments have shown that these compounds can form in interstellar ice analogs when exposed to ultraviolet radiation and cosmic rays. If 3I Atlas contains similar compounds, and if comets like it were common in the early solar system, then the case for exogenous delivery of life's building blocks becomes much stronger. It also raises the possibility that life could have started elsewhere and been transported here, or that similar processes could be occurring around other stars right now. The implications are staggering. The James Webb Space Telescope is scheduled to conduct additional observations after perihelion, the point of closest approach to the Sun. JWST's infrared capabilities are ideal for studying the thermal emission from the nucleus and the composition of the coma. Ultraviolet spectroscopy, which JWST can perform with certain filters, will help refine the inventory of volatile species. The goal is to detect molecules like hydrogen cyanide, methane, ethane, and possibly even more complex organics like formamide or glycine. Each detection adds a piece to the puzzle of where this comet formed and what conditions were like in its natal environment. If the chemical profile is radically different from solar system comets, it would confirm that planetary system chemistry is highly variable, shaped by local factors like stellar metallicity, disk temperature, and the presence of nearby massive stars. If, on the other hand, the chemistry is similar, it would suggest a degree of universality, a common set of processes that operate regardless of where you are in the galaxy. Now, I want to pause here and ask you a question. What do you think is more likely? That this comet's unusual chemistry is simply a product of a different stellar environment, or that there is something more exotic going on, something we have not yet considered? Drop your thoughts in the comments. I am genuinely curious to see where the audience stands on this, because even among scientists, there is no consensus yet. While mainstream researchers are focused on the natural science, a subset of speculation has emerged on social media and in certain academic circles. These ideas are bold, provocative, and, it must be said, highly uncertain, but they are worth examining if only to understand the full range of possibilities being discussed. Avi Loeb, the astrophysicist I mentioned earlier, has a history of proposing unconventional hypotheses about interstellar objects. After Oumuamua, he suggested it might be a light sail, a piece of alien technology powered by radiation pressure. The idea was controversial and remains unproven, but it sparked important conversations about what kinds of evidence we would need to identify artificial objects in space. Now, with 3I Atlas, Loeb has floated another possibility. He notes that the anti-tail, the swarm of particles extending 60,000 kilometers from the nucleus, could in principle consist of small, solid objects rather than ice fragments. He has speculated, and this is purely speculative, that these could be related to von Neumann probes, hypothetical self-replicating machines that an advanced civilization might send out to explore the galaxy. The idea is that such probes could travel between stars, using local resources to build copies of themselves, gradually spreading across vast distances. If 3I Atlas were a carrier for such probes, the anti-tail might represent a dispersal mechanism, scattering smaller units as the parent object passes through a star system. Loeb has also pointed to the comet's estimated mass, potentially billions of tons, and suggested that the size and composition could be consistent with a constructed object, a mothership of some kind, rather than a natural comet. Let me be very clear, there is no direct evidence for any of this. The spectroscopy, the imaging, the dynamical models, all of it is consistent with a natural cometary body. But Loeb's point is that we should not dismiss possibilities simply because they seem unlikely. Science advances by testing hypotheses, even uncomfortable ones. If 3I Atlas were artificial, what would we expect to see? Perhaps unusual emission spectra, lines that do not correspond to known molecules. Perhaps geometric structures in the nucleus, shapes that are too regular to be natural. Perhaps anomalous changes in trajectory that cannot be explained by outgassing alone. Some researchers have suggested that if fragmentation occurs during the close approach to Earth, and if any of those fragments can be studied in detail, we might detect anomalous particles or materials that do not fit the natural comet model. The probability of such an outcome is extremely low, but the scientific method requires us to remain open to data-driven conclusions. Other scientists have explored scenarios where the comet could carry traces of technological artifacts, not because it was built, but because it encountered them during its long journey. Imagine a comet passing through a debris field left by an ancient civilization or skimming the outer layers of a Dyson swarm, a hypothetical megastructure built around a star to harvest energy. In such a scenario, the comet might accumulate unusual dust particles, isotopic anomalies, or even microscopic machinery. These are extreme edge cases based on speculative models, but they illustrate the breadth of thinking that interstellar objects inspire. The key is to separate informed speculation from unfounded claims. On social media, there have been attempts to link 3I Atlas to the WOW signal, the famous radio burst detected in 1977 that has never been explained. The logic is tenuous at best. Both are mysterious. Both are from space. Therefore, they must be connected. Scientists have been quick to dismiss this. The WOW signal came from the direction of Sagittarius, and there is no evidence it had anything to do with a physical object, let alone a comet. 3I Atlas's trajectory does not intersect with that region of sky, and its radio emissions, if any, would be thermal or molecular, not the kind of narrowband signal we associate with potential technosignatures. The point is that while bold hypotheses are valuable, they must be grounded in evidence and subject to rigorous testing. What we do know with high confidence is that 3I Atlas is going to be a major focus of observational astronomy for the next several months. Ground-based telescopes around the world are scheduling time to track it. Space telescopes are coordinating multi-wavelength campaigns. Amateur astronomers are contributing light curves and position measurements. The data being collected now will be analyzed for years, if not decades. We will map the comet's rotation, measure its spin axis, characterize the composition of different outgassing regions, and model the forces acting on the nucleus. If fragmentation does occur, we will study the size, distribution, and velocity of the pieces, looking for clues about the internal structure. Was the nucleus a solid monolith, or a rubble pile held together by weak gravity? Are there layers of different ice composition, remnants of the comet's formation history? Every measurement refines our understanding. The long-term effects on the solar system are minimal. The comet's trajectory will carry it past Earth, past the Sun, and eventually out beyond the orbit of Neptune, where it will fade from view. In a few thousand years, it will be in interstellar space again, continuing its journey across the galaxy. But the knowledge it leaves behind will be permanent. We will have learned about the chemistry of another star system, about the survival of comets in interstellar space, about the diversity of planetary formation processes. We will have tested our instruments and our models, and we will have been reminded that the universe is full of surprises, that objects can travel between the stars, carrying information from places we may never visit. If this story resonates with you, if you believe that supporting in-depth science coverage helps push the algorithm toward more educational content, please consider hitting the like button. It genuinely makes a difference in how widely this kind of reporting gets seen, and in turn, it supports the broader effort to make complex science accessible and engaging. Looking ahead, the February 2026 release of the full JUICE spectroscopy dataset will be a major milestone. That data will include high-resolution spectra covering a wide range of wavelengths, allowing scientists to identify molecular species that are currently below the detection threshold. If methanol is elevated, are other alcohols also present? What about formaldehyde, acetaldehyde, or more complex organics? Are there isotopic ratios that can tell us about the temperature and radiation environment where the comet formed? Isotopes are powerful tracers. For example, the deuterium to hydrogen ratio in water ice can reveal whether the ice formed in a cold, outer region of a protoplanetary disk or closer to the star. Similarly, the carbon-12 to carbon-13 ratio can indicate the degree of chemical processing the material underwent before freezing out. If 3I Atlas has isotopic ratios that differ significantly from solar system comets, it would be direct evidence that its formation environment was distinct, shaped by a different star with a different history. The meteor shower scenario, while speculative, is also being modeled. If fragments from the comet enter Earth's atmosphere, they would create meteors with unusual properties. The entry velocity would be higher than typical solar system meteoroids because the comet is on a hyperbolic orbit, meaning it has excess speed relative to the Sun. That higher velocity translates to brighter, faster meteors. The composition would also be different, potentially leaving spectral signatures in the meteor trail that do not match known meteor showers. Detecting such an event would require coordinated observations by meteor networks, both professional and amateur. Organizations like the American Meteor Society and the International Meteor Organization are already on alert, encouraging observers to report any unusual activity in mid to late December. Even a handful of confirmed interstellar meteors would be scientifically valuable, providing direct samples of material from beyond the solar system. Brian Cox's comment about the comet wandering for billions of years is worth revisiting. Think about the timeline. 7 billion years ago, the universe was roughly half its current age. Galaxies were more compact, star formation rates were higher, and the Milky Way looked different than it does today. 3I Atlas formed in that era, in a stellar system we will likely never identify. It was ejected either by gravitational interactions with planets or by a close encounter with another star, and it began drifting. For billions of years, it moved through the interstellar medium, buffeted by stellar winds, irradiated by cosmic rays, occasionally passing through molecular clouds. It survived all of that. Most comets would not. Cosmic rays would erode the surface, heat would cause sublimation, collisions with interstellar dust would sandblast the nucleus. The fact that 3I Atlas is still active, still outgassing, still shedding material, suggests it is either very large with deep reservoirs of ice, or it spent most of its journey in a relatively benign environment, shielded from the worst of interstellar hazards. Either way, it is a survivor, a relic from an ancient epoch. The question of whether comets can seed planets with the chemistry for life is not new, but it gains urgency every time we discover a new interstellar object. If our solar system was visited by comets like 3